time t is given by a twice differentiable function h, where h of t is measured in meters and t is measured in years. Selected values of h of t are given in the table above. Okay, check out the table. We're given years and we're given height of this tree. A. Use the data in the table to estimate h prime of 6. Using correct units, interpret the meaning of h prime of 6 in the context of the problem. A is asking for an estimate of h prime of 6. Well, an estimate of a derivative is an average rate of change, or slope, change of y over the change of x. Since we're looking for an estimate when time is 6, the best estimate is to look on the interval from 5 years to 7 years. So I just did the change in the height, 11 minus 6, over the change in time, 7 minus 5, and that gave me 5 over 2. Okay? H prime of 6 itself is the rate at which the height of the tree is changing in meters per years at t equals 6 years. When they ask for units, you have to give units, otherwise they will take off a point. B. Explain why there must be at least one time t for the interval 2 to 10 such that h prime of t equals 2. B. Right when you read it, I hope you think, ooh, this is going to be one of those existence theorems, like the intermediate value theorem, or the extreme value theorem, or the mean value theorem. This, in fact, is the mean value theorem. Remember, whenever you use one of these existence theorems, you have to state the precondition. In this case, precondition for the mean value theorem is that the function is differentiable, which we were told. And the mean value theorem is basically saying, hey, if the average rate of change from 3 to 5 years was 2 meters per year, then there had to be some point during that time when the instantaneous rate of change of the tree was 2 meters per year. That makes intuitive sense. That's the mean value theorem. Kind of like if you're driving to a friend's house and your average speed is 50 miles an hour. Well, you had to have gone 50 miles an hour at least one point. That's the mean value theorem. C. Use a trapezoidal sum with the 4 subintervals indicated by the data in the table to approximate the average height of the tree over the time interval 2 to 10. C is not on the 2020 AP exam because it's asking for an average value, but we did learn this. If you remember, the average value is the integral. In other words, you're adding up an infinite number of those heights and you're dividing it by the change in your time, right? So that's where the 1/8 comes from. But you do have to know how to estimate the area under a curve by doing trapezoidal sums or Riemann sums. This is asking for a trapezoidal sum. And if you recall, to find the area of a trapezoid, you add the bases. So in this case, it's the height, 1.5 plus 2. And you divide that by 2. You're finding the average of the bases and then times your change in your years here. Okay? So if we look at our data, so it's going to be 1.5 plus 2 divided by 2, average of the bases, times the change in your time, which is 1, plus 2 plus 6 divided by 2, times the change in your time, which is 2. The next trapezoid area is going to be 6 plus 11 divided by 2, your bases add together, divided by the change in time, which is 2. The next trapezoid area, 11 plus 15 divided by 2, times 3, your change in your time. And you can see that right here. Okay? But again, average value is not going to be on the exam this year. D. The height of the tree in meters can also be modeled by the function g, given by g of x equals 100x divided by 1 plus x, where x is the diameter of the base of the tree in meters. When the tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate of 0.03 meters per year. According to this model, what is the rate of change of the height of the tree with respect to time in meters per year at the time when the tree is 50 meters tall? Let's dive in. D is a related rates problem. I hope that you thought related rates when you heard it. It's talking about the relationship between the rate at which the height of the tree is changing as the diameter is changing, right? So related rates. So with related rates, we always want to come up with an equation. They gave us one, so that's good. G gives us the height of the tree. X is the diameter. We want to take the derivative of this with respect to time. So here we go. Derivative of G with respect to time is 1 dg dt. Chain rule, right? We've got a quotient, so we're going to use the quotient rule. The derivative of 100x is 100 times the derivative of x, which is dx dt. So that's the derivative of the top times the bottom as it is, minus the top as it is, times the derivative of the bottom. The derivative of the bottom is just 1 dx dt over the bottom squared. All right, we're looking for this. We're looking for the rate at which the height changes when my height is 50 meters. And they do tell us dx dt. They tell us that is, let's see, 0.03 meters per year. What they don't tell us is x, and clearly we need to know x. But they gave me 50 for g. They gave me this equation right here. So I can just set up an equation here. I'm going to replace this g with 50 and solve for x. In other words, I'm going to find the diameter of the tree that gives me a height of 50. I'm going to cross multiply. 50 plus 50x equals 100x. Subtract, I get 50x equals 50, and nicely x is 1. So x equals 1. So that's not that bad. So I just moved that up so you could see that a little bit. My x was 1. So now I'm just going to plug everything in. I'm going to plug everything in. So I have 100 times dx dt, which is 0.03, 1 plus 1, which is 2, minus 100 times 1 times dx dt, which is 0.03, over 1 plus 1, also known as 2 squared. Now I think when you look at the rubric, they actually factored out the dx dt just to make the computations easier. But either way, it's fine. If you stick this in your calculator, you should get 3/4. Okay? So at this moment, when the tree is 50 meters high, the height of the tree is growing 3/4 of a meter per year. Pretty cool.